Hello, and welcome to this talk about our paper Systematic Analysis of Randomization-based Protected Cache Architectures. My name is Antoon Purnal, and I'll be presenting joint work with Lucas Giener and Daniel Groes from Graz University of Technology, as well as Ingrid Verbouwede and myself from IMEC COSIC at KU Leuven. Now, one of the reasons why this talk is the way it is because of a curve like this. And I'm not talking about the elephant in the room, and I'm also not referring to a few other recent events, but maybe when you know that there's actually two curves, that they originate around the 60s, and that the important bit is the gap between the curves, then you might suspect that what's being depicted here is the performance gap between CPU and memory. Yes, indeed. To bridge this gap, modern CPUs are equipped with a cache hierarchy, which makes programs run faster by avoiding many round trips to memory, but it also endows them with the ability of spying on one another through a timing side channel. One line of work that aims to tackle this problem is that of randomized caches. Now let's have a look at what exactly is being randomized. Nowadays, caches are typically set associative, meaning that they're organized as an array of cache lines along sets and ways. Typically, the number of sets is a power of 2. Each memory block can only be installed in one set, and this set is chosen by slicing a portion of the memory address called the set index. Within the set, the line can be installed in any of the ways, and lines mapped to the same set are called congruent. First generation randomized caches, like Caesar or TSC, preserve the set associative structure of the cache. And when an address A1 comes in, the set index for this address is derived by a randomization mapping. To avoid the mapping being learned over time, it's equipped with a key, which changes over time through a process called rekeying. And when the key changes, the mapping changes, and the same address gets mapped to a different set. Unfortunately, these designs are insecure in light of new advances in finding congruent addresses, meaning that rekeying would have to be performed impractically often. To overcome this problem, two concurrently proposed designs add an extra layer of unpredictability. Caesar S divides cache sets in 2 or more partitions and adopts a different randomization mapping in each partition. When an address is installed in the cache, one of the partitions is randomly selected, and the address is indexed in this partition according to the output of the mapping. Scatter cache operates in a similar fashion, but maximizes the number of partitions by computing an independent index for every way. Prior analysis of Caesar S and scatter cache claims to tolerate years or days of continuous attacks, respectively, before an attacker can construct a single useful eviction set. And we'll get to what exactly that means later. In our work, we invalidate these claims by proposing a generic technique called Prime+Prune+Probe to efficiently produce eviction sets in randomized caches. The remainder of this talk is organized in 3 parts, and at the end, you'll know how to generalize traditional cache attack concepts to randomized caches, how Prime+Prune+Probe works and how it maximizes the probability of catching victim cache activity, and finally, why the randomization mapping itself is of crucial importance to the security of the entire design. Let's start by defining the system along with some useful objectives for the attacker. The core of the randomized cache is the randomization mapping, which is a deterministic but random-looking function that takes an input address and produces a randomized output to index the address into the cache. Now it actually produces not one but p outputs, one for each partition, and if a partition contains more than one way, the replacement policy determines which line in the set is to be replaced. In this work, we consider random and LRU replacement policies. The unpredictability of the mapping is provided by a secret input k, which can be changed at runtime through a process called rekeying when a specific condition has been met. Importantly, some designs also feature a security domain input to the mapping, S, which ensures that different security domains experience a different mapping, even when indexing the same address, as in the case of shared memory. Duplicating shared memory in the cache like this eliminates shared memory attacks like flush and reload by design. We first study this model generically before instantiating it to specific designs like Caesar S and scatter cache. Our focus will lie on partitioned caches with attacker and victim in different security domains, which is the strongest operating mode in this model. Now, what can an attacker do in this case? Well, the cache is still shared, so an attacker can still measure contention with the victim for cache resources. In traditional caches, an attacker typically doesn't monitor the whole cache, but narrows it down to a smaller contention domain like a set. To do this, she first finds an eviction set containing addresses mapped to the same cache set, and by measuring the time it takes to access the elements of this eviction set, an attacker can learn whether the victim has also accessed a congruent address. Let's see if we can transpose this strategy in any way to randomized caches. Consider a victim address X on which the attacker wants to spy. She could try to find addresses that are congruent with X in all partitions simultaneously, but the probability of this happening plummets exponentially, making it completely infeasible. Instead, Werner et al. Generalize eviction using partially congruent addresses, which collide with the target address X in one partition only. So in this example, G1 contains addresses that collide with the target in the blue partition, G2 for the orange and G3 for the brown, and this means that if X is currently cached in the blue partition, the only addresses that have a shot at evicting it will come from G1. This is generalized eviction. Generalized eviction is probabilistic. In the paper, we derive the success probability as function of the randomized cache instance, but for this talk, suffice it to say that generalized eviction can be made reliable enough by sizing the set appropriately. In the second part of this talk, we explore how to collect such partially congruent addresses. As a baseline, an attacker could modify prime and probe from traditional caches and prime one guess address, wait for the victim access to a target X, and then probe it. If she's lucky, then X will evict the primed guess and she will observe this through a high access latency. If she's unlucky, then the guess is no good. And if she's very unlucky, then the guess actually is partially congruent with X, but X is assigned to another partition in which it's not congruent. This approach has several issues, the first being that it's very slow. For random replacement, every time the victim access occurs, the attacker is only lucky with probability 1 over n, where n is the total number of lines in the cache. The second issue is that in the worst case, the probability of catching the victim event, or being lucky, is 0. For instance, for LRU replacement, even if the victim access is mapped to the same set in the same partition as the guess, the attacker will not observe it. So we would like to prime more than one guess every time. Let's say we're priming k guesses. At first sight, this is also flawed, because as k grows, the attacker's guesses will self-evict, and an attacker probe cannot distinguish whether a cache miss truly results from a victim access or spuriously because of this self-eviction. To eliminate this source of false positives, we propose the concept of pruning, giving rise to the Prime+Prune+Probe technique. After priming the cache, the attacker keeps accessing the prime lines until they no longer exhibit self-eviction. And this keeps the guesses that were not self-evicted in place, while the self-evicted addresses are forced to be installed again at a potentially different location. After some time, the cache state settles, and if it doesn't, pruning can become more aggressive and remove these self-evicted lines. And after the prune step, the attacker occupies k prime, say, lines in the cache, and the probability of catching the victim access is much higher than before. Prime+Prune+Probe continues in iterations, starting from an empty set and incrementally adding addresses that have demonstrated contention with this victim address X. And this continues until enough partially congruent addresses have been obtained. The paper features a quite extensive statistical and experimental analysis of this Prime+Prune+Probe, but in the interest of time, we state the main takeaways and refer to the paper for details. For one, the target line X can already be cached, which complicates catching further accesses to it. And we explore whether the attacker should expend effort to evict it first or to just continue Prime+Prune+Probe as usual. We also discuss optimizations to Prime+Prune+Probe and, in particular, how to accelerate the search for new addresses using the ones that are already found. We also cover how the number of invocations of the victim can be significantly reduced by pre-selecting candidate guesses. And finally, as a data point for an end-to-end attack, we mount the well-known first-round attack on AES t-tables, which is a challenging target in a randomized cache, as there are many sensitive cache lines that should be distinguished from one another, and they each encode only statistical information. To overcome this challenge, we rely on specially crafted inputs and recover the half keys in the order of minutes. To test the efficiency of Prime+Prune+Probe, we consider an 8 megabyte 16-way set associative cache as an example, which is a representative instance for modern last level caches. The horizontal axis covers the instances of our model, and the y-axis represents the total number of cache accesses required in log scale, where n is the total number of lines in the cache. The total number of cache accesses is estimated as the number of accesses by the attacker, as well as those by a modestly sized victim program, which we assume performs around 1,000 accesses. For Caesar S, we can see that 3 instances are proposed that rekey, respectively, every 100n, 200n, or 1000n cache accesses. The 1000n instance, which is the least conservative one, claims a resistance of 68 years of continuous attacks based on full congruence, but with Prime+Prune+Probe we can find high-quality generalized eviction sets well within the rekeying period. If an attacker can live with less accurate sets than 90% or 50% eviction rates, the number of accesses for Prime+Prune+Probe drops even further. Scattercache does not propose a specific rekeying period, but Prime+Prune+Probe outperforms their analysis by a few orders of magnitude. Note that Caesar S and Scattercache can still be made secure by selecting a conservative rekeying period, but Prime+Prune+Probe significantly reduces the security margin. The final part of this talk explores the randomization mapping itself, for which some designs have proposed a custom function for low latency. I will now illustrate the pitfalls of this approach through a case study of Caesar and Caesar S, ultimately leading to a full break. The mapping in question is a 4-round Feistel network, where the round function f is composed of XORs and bitwise permutations, which is very hardware friendly but also linear. And if the round function is linear, then the whole construction is linear, which makes it especially vulnerable to the propagation of differences. So if we take the difference between two inputs and define delta functions that describe how these differences propagate through the round function, we can propagate them all the way to the output, leading to an expression which we call the shortcut equation. And this equation permits to find eviction sets without any accesses, because, well, when are two addresses congruent? When they have the same output index bits. Or in other words, when the difference of these bits is 0. And with this equation, we know which differences to apply to the input to obtain a 0 output difference. Importantly, this equation is independent of the key, which means that eviction sets constructed in this way are immune to rekeying. The equation is also independent of the input itself. It only depends on the input differences. So an eviction set for one target can be trivially transposed to an eviction set for any target. And finally, in Caesar S, each partition uses the same mapping but with a different key. But due to our key independence, actually addresses congruent in one partition are congruent in all partitions, and we've moved right back from partial congruence to full congruence. All of this goes to show that even though the randomization mapping is mostly hidden from the attacker, its instantiation is crucial, as otherwise the security properties of the design can quickly collapse. To conclude, we proposed Prime+Prune+Probe as a generic technique to find probabilistic but reliable eviction sets in the presence of randomness. We also showed an end-to-end attack on AES and highlighted the vital importance of a proper randomization mapping. Thank you for your interest in our work, and for more information, please check out our paper that appears at SMP 2021.